In this video, we're going to look at two more shortcuts that we could use to prove that triangles are congruent. The first, SAS, stands for side angle side. The second, HL, stands for hypotenuse leg. Consider the relationship involving two sides and the angle that they form called the included angle. For example, let's create triangle DEF such that DE is 2 inches, DF is 3 inches, and the included angle, that would be the angle in between them at D, has a measure of 35 degrees. And then let's answer the question, how many different triangles can be made? All right, so to set things up, I went ahead and already drew a picture here. DE is 2 inches. That's going to be up here. DF is 3 inches, which we have there. And then the angle that's right between them is 35 degrees. Okay, so that makes this D. This point right here would be E. This would be F. All right, so given those pieces, we're asked the question, how many different triangles can we build? Well, the length of that is set. That's not going to change. So endpoint F is located here. The length of this is also set. Okay, endpoint E is going to be located there. And because this angle is already set at 35 degrees, we can't imagine opening these two sides. We can't make them go any further apart. We can't make that segment that would connect EF any bigger or smaller than just connecting them. Which means that you can only make one. You can only make one triangle given these pieces here. All right, so from that demonstration, we get the side angle side, or SAS congruence conjecture. If two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then the two triangles are congruent. All right, so we have the side congruent shortcut, and now we have the side angle side shortcut. Visually, what you're looking for here is going to be two sides and the angle that would be located right between it. Okay, so if two triangles have those matching parts, you can go ahead and assume that they are congruent. All right, let's go ahead and do a proof that uses side angle side. We're asked to prove that triangle ABC, that's ABC, prove that ABC is congruent to CDA, to CDA. Okay, our given information, BC is congruent to DA. BC is up here, it has that single marking. DA is right here, that also has a single marking, so that's shown in the picture. The other given information is that BC is also parallel to AD, and you're going to know that because it has the little arrows that are on there. Okay, so for our proof, both of these pieces of information, those are given, so we'll go ahead and write that down. All right, and then what we need to do is come up with enough information that's going to use that shortcut, side angle side, and prove that the triangles will be congruent. Okay, so you've already got a pair of sides, right? You've got these two. We need an angle and we need another side. Okay, and what I like to do when I write the proofs is attempt to write the shortcut in the right order. So if I'm going to start with a side and I'm anticipating using the shortcut side angle side, what I'm going to do is try and get an angle next. Okay, so BC is parallel to AD. Okay, these are parallel. AC, that is actually a transversal, right? It's going to cross through BC and AD. You might need to imagine that these extend out further, but this would be a transversal. And if you have a transversal with parallel lines, you're going to get congruent angles. You're going to get congruent corresponding angles. You're going to get congruent alternate interior angles and alternate exterior angles. The ones that we're going to be looking at are going to be right here and here. I'll go ahead and call that angle 1 and call that angle 2. Okay, so angle 1 is going to be congruent to angle 2. All right, so angle 1 is congruent to angle 2. Reason? It's two things here. One, the lines are parallel, which that was mentioned in line 2, so we don't need to bring that up again. But because those lines are parallel, these two angles, which we can call alternate interior angles, will be congruent. They're going to be congruent. All right, so that is going to give us a couple of angles. All right, so in the top triangle, we've got at this side with that angle, which is right next to it. The bottom one, we've got this side with the angle right next to it. The third piece that we need is going to be the shared side. It's going to be that shared side AC. All right, so for the top triangle, I'm going to go ahead and call that CA. I'm going to draw it that way. So CA, so that it comes from the included angle. All right, so CA is going to be congruent, and if I look in the next triangle, I'd have to match that up as AC. It would have to be AC. That way I'm extending from the included angle out. Everything matches up that way. All right, so the reason that these two are congruent is the reflexive property. The reflexive property. All right, so then 5, we actually have enough information now. We've got two sides and the angle, which happens to be included. That's important. We have two sides and an included angle being congruent between the two triangles. That means we can go ahead and conclude. We can go ahead and conclude that triangle ABC is congruent to triangle CDA. The reason is going to be side, angle, side. Next, what we're going to do is look at a case that doesn't work, the side-side angle case. Okay, so it's a little bit like the one that we saw before because we do have two sides and we have an angle. However, the angle is not included. It doesn't sit between the two sides. All right, let's take a look at the picture here. We've got two sides and an angle, but that angle is not located between the two sides. Okay, so this will be side, side, angle. All right, now if you ever run across this case, you're going to have to say that it's an invalid shortcut because you can actually get two different pictures. All right, so let's see how that works out. Both pictures have a base of AC. Of course, the base over here is going to be longer. They also both have an angle A. That is the same size. That'll be the angle that we're referring to here. And they also have a segment extending from A to B. That would be the same length over here. So that would be one of our sides. And then you have a second side that is also congruent. All right, but in the organization of these pieces, that angle is not located between the given sides that we have. Okay, so let's see what happens. Assume that the base is going to be horizontal, that we're not going to change the direction on that, just let it be. But we don't know the length of it, that hadn't been provided. Okay, this angle is going to tell us that we do need to move in this direction from that base. We got to move in this direction to point B, and that length is set. You're going to see that it's set over here. So this angle, that direction that we get, the length of that segment is going to match up over here. At the end of B, you have the other congruent segment. You have it here. But as you can notice in the two pictures, because we don't have a set angle between B, you can either draw that segment sort of in towards A, or you can draw it out away from A and end up over here. Okay, overall, they do have the same three corresponding parts. They both have angle A. They both have this segment extending from A. They also both have that segment extending away from B. But you end up with two different triangles. There is one case where side-side angle does work, but it's a special case that we refer to as hypotenuse leg, or HL. All right, let's take a look at the picture with respect to side-side angle. All right, in the two triangles, they both have a double mark side, they both have a single mark side. Those match up. They also have an angle. They also have an angle that's congruent. However, that angle is not located between the two sides. So this is not side angle side. This best fits side side angle. However, that angle is a right angle, which means that we have right triangles. And if we have right triangles, we can do something called Pythagorean Theorem, which would work in this case. We have a hypotenuse, we have a leg length. Well, you might not know what the numbers are, but you have a certain hypotenuse and you have a certain leg length here that match the hypotenuse and the leg length over here. So if you did have those values, you could do Pythagorean Theorem, and you could figure out that these two sides, the bases, that they would be congruent to each other, which means by default, you could actually call this side, side, side. Okay, we don't need to go through the whole process of doing that work and getting two side, 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 because it would always work. So we get to refer to this as hypotenuse leg, or HL. For example 2, let's go ahead and write a proof that uses hypotenuse leg. What we're asked to do here is prove that triangle WYZ, so there's WYZ, it would be that one, is congruent to triangle XZY. That would be this one over here. Okay, what might actually help here is if we separate the pictures because we got some overlap going on here. Okay, so I'm going to do a quick sketch. We got W, we got Z, and Y. Okay, and then over here, we'll have X, we'll have Y, also have Z. So by separating those, it might be easier to match certain things up. All right, given information, WY, which is right here, is going to be congruent to XZ. Okay, so we can add some markings there. WZ is perpendicular to ZY. WZ is perpendicular to ZY. That means that we have a right angle. Okay, that's that hypotenuse leg about to show up. XY is perpendicular to ZY. So here's XY, there's ZY, and there's your other right angle. All right, so we got those matching up. And that would be all of your given information. All right, so let's go ahead and just fill those in as given. Go ahead and knock that part out. All right, so I want to do this by hypotenuse leg. The hypotenuse is right here, right? The hypotenuse is right there. That would be line 3. We don't need to state right here that this is the hypotenuse, but in the picture it is a hypotenuse, so we've got that part. What we need is a leg length. Either WZ is congruent to XY or ZY is congruent to ZY. Well, when you read them out loud, you probably figure out what it is. These two have to be congruent, right? They were this segment right here, which in the original figure is a shared segment. So ZY is going to be congruent. ZY, we're going to need to write it backwards here, is congruent to YZ because of the reflexive property. All right, so that will be a leg length. We got the hypotenuse part, we've got the leg length part, so now we can go ahead and say that triangle WYZ is congruent to triangle XZY, and that is by hypotenuse leg.
Later, blah.